Hello community! Today we have a unique opportunity to compare science agent between Stanford University and MIT. Because we have here from Stanford University a paper, September 6, 2024, Can LLMs Generate Novel Research Ideas? And just September 9th, so after the weekend 2024, we have from MIT Science Agent, Automating Scientific Discovery Through Multi-Agent Intelligent Graph Reasoning. So, really interesting here, two beautiful papers, and we're gonna enjoy and we look at them together. Now, you have heard that this is a study a little bit hyped. Why? Because there's a simple result and it tells them, hey, AI are better than humans. Now you know that this is not the correct results because what they really did, they had 7 topics. Those were the topics. And then they had human expert and AI agents. And you're not going to believe it, the task was to come up with a new research idea. And 49 human ideas were generated, and by a blind review by human expert, they were evaluated but based only on their novelty. And the AI, condition 2, also AI ideas, and they were also evaluated what the AI created here on research ideas, and you see the AI was rated with a higher novelty score. And of course, if you have humans and AI working together, we have a little bit higher novelty score. So we have 79 expert human researchers to perform here a blind review of those 49 ideas from each of the 3 conditions, expert, AI, and AI plus human. You see these figures exactly here in the novelty, where human is yellow, AI is light blue, and AI plus a re-ranking is dark blue. So you see out of these 4, in 3 out of them, a human are not performing better than AI. Only in feasibility, we have a little tiny touch better performance by the humans. But in the overall evaluation that you see here, this is not a result that is currently hyped on the internet. Yes, humans are less intelligent than AI, which is nonsense because as we will look at the experiment, they only did here something for an idea generation, and I will show you the tasks. What is interesting, highly interesting, we have 2 studies and we compare them side by side, and we discover reading both studies here, and this is here close to I think 100 pages and this is 80 pages. We understand that there's a common thing in both studies. Here we have the core idea of an idea generation agent, and here we have the idea of science agent here for scientific discovery, doing this automatic with a graph reasoning and an LLM. So this is now real interesting. Now, let's start here with Stanford University. We have the idea generation agent, beautiful. But what was the topic? The topic was a specific research topic, novel prompting methods that can improve the factuality and reduce the hallucination of LLMs. That's the task. Now, Stanford decided to make this a 5-point process. The first is, of course, we have here an API. So we have a function call to Google Semantic Scholar to the external publication, and they received here for each specific topic here with a keyword query, a paper query, and a reference query, about 120 papers, and the top 20 papers they kept. And they rated for relevance, empirical nature, and inspirational potential. Interestingly is, if you read this, they refer here in their function calling in the API to replug, where this was also here with Michihiro at the time here at Stanford. Have a look at this. This is quite a nice thing. For the LLM in the agent, they used here Claude 3.5 Sonnet as the backbone model for the agent. Now let's talk about the research topics that were examined. I told you there were 7 things: bias, coding, safety, multilingual, factuality, math, and uncertainty. But now, how diverse was the task where the human did not succeed? and AI triumphed over the human race? Well, try if you see here a common thing. Novel prompting methods 2, novel prompting methods 4, novel prompting methods 2, novel prompting methods 2. So you see, we're only talking about prompt engineering. And if I tell you that the agent created 4,000 statistical new ideas and the humans only created 49 ideas, and then from those 4,000 they were condensed down to also 49, and then we had a little bit of a novelty advantage for AI. So now you understand the scientific content of this comparison. Second step was idea generation. So as I told you, up to 4,000 seed ideas per topic. Our agent generates a large pool of ideas with the understanding that only a fraction of them will be high quality. As we will see, of those 4,000, only 200 made it into, could be maybe a good idea, and then was further reduced. So you see exactly what is happening. Statistically, 4,000 ideas, as crazy as possible. And yes, statistically, you will have some good ideas in this body of seed ideas. Generation process here included title and abstract of the top ranked paper retrieved in the steps, demonstration example, I will show you one in a second, and a prompt for the LLM to avoid repeating previous ideas. The distribution of our 49 human expert that vote, 1 postdoc, 36 PhD, 9 masters, and you get it. And for the review process, we had 79 human expert, and this was their professional distribution. Now let's look at what the humans and the AI had to come up with a new project proposal, a new project idea. And it was a simple JSON file, a title, a problem statement, a motivation, a proposed methodology, a step-by-step detailed experimentation plan, test case examples, and a fallback plan. So, not as easy as you might imagine. Plus, they were given here, especially the AI system, a complete project proposal, a complete filled out demo example, so the AI could understand exactly what was expected from the AI. This was the golden copy, this was to be generated. Step 3 was deduplication and filtering. And now, beautifully, we have back sentence transformer, SBIRD. So what they did, goal was easy. We want to remove everything that we already have, no duplicate ideas. The system performs deduplication by encoding all generated ideas using sentence transformers and calculate the pairwise cosine similarity between the idea vectors in the vector space in the embedding, and everything above a similarity score of 0.8 is considered a duplicate and removed, and here only 5% of the original pool of ideas remains now as unique candidates. And if you want to go have a little bit more detail from the SBIRD, from the sentence transformer, where I have a complete playlist with 50 videos, they used here the old mini LM that I already have in my videos. Now, I found it interesting to see, okay, so if we the AI generates 4,000 ideas of one topic. They did now here this beautiful graph, and this here showed us here non-duplicate percentage. So you see, at 1,000, I would say we are at 8% non-duplicate, but at 4,000, I don't know, less than 1%. So the non-duplicate rate goes down, 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 asymptotic to 0. But it is not at 0, because as you can see here, if we look at this graph here, where we also have our 4,000 steps on the x-axis, but we have now the accumulated non-duplicate ideas, you see even between 3,000 and 4,000, there's a little bit here of new ideas, new non-duplicate ideas generated. So an AI can generate, 8,000, 20,000 new ideas, and then you just have to select and filter out. Step number 4 was the ranking of the ideas. simple objective. We want to identify the best examples that we got. So what is the process? The agent uses a pairwise comparison to rank ideas. So theoretically, we have a lot of opportunities how we do the ranking. No? They decided to go with a pairwise ranking. So they take here one idea and another idea, and they do not give a score 0.6 here and 0.8 over there, but they just say, hey, of this two paper, this is the better paper. And then they just go through the complete, and then they have exactly here the winner is. Now, the ranking model in our agent now was trained, of course, here by publicly available review data of 1,200 submissions to a particular AI conference, how the humans, evaluator and reviewer, what they wrote, their specific wording, what they thought about the topics. So we had here quite a nice training data set of 1,200 project-specific evaluation, along with the review scores that were given by the human evaluator. Now you understand that I showed you here in this video where I showed you the new core of AI agents. We have Stanford and MIT also here. End of August 2024, they presented us here a new AI-driven review system. And what they did, they especially trained here an agent to behave exactly like here a reviewer of one of those conferences. And I showed you here in this video how it works, and I've given you a demo, an example, and I showed you if you upload a PDF or if you upload your PDF, your scientific work that you want to publish, this agent here is really nice. It gives you here an almost official review by here an international conference review score. So you see, you have a lot of possibilities to rank this. Just that you know, here in this particular case, they used pairwise comparison. Yeah, and the top 10 ranked ideas were selected for further evaluation. And this is now step 5, our final step. Ensure that the top ranked ideas are both novel and feasible for a real-world execution. If you would have to go to the moon and then jump to Venus to do your experiments, it is not really feasible. And novel, this is easy, you just have a look here at the existing literature. Is now this AI-generated idea or this human-generated idea really novel? You can do this real simple. And there you have it. This is it. Now there was a little trick, and I don't know if you noticed this. In our idea generation agent, and we can have this as a major agent, and as you noticed, sometimes I try to break out in a multi-agent, no, but they did it here in an idea generation agent. They had a problem here with the maximum output length, the limit length of an LLM, because you know the context window of whatever your LLM is somehow limited. And they did not went with Gemini with 1 million or 2 million context length, token length. So if you only have 200K and you generate 4,000 ideas in a complete template structure, so you run out simply of token space. And they had an idea to generate, before they generate the real idea, they generate a seed idea. So this is something like a prototype idea. And they had here the template for this. For the seed idea generation, you had the title, the problem, the existing methods, the motivation to do this, the proposed method, and the experiment planning. You see, simplified, shorter, but now 4,000 things could fit maybe into 200,000K context length. And there you have it. This is our 5-step approach: paper retrieval, idea generation, 4,000 seed ideas, deduplication, idea ranking, and the final filtering for feasibility and novelty. Then you had some overarching evaluation criteria: novelty, excitement. Now I have to say, if you ask me about my excitement early morning, if there's a good paper, I'm very excited. If you ask me close to midnight about my excitement about a particular AI research paper, okay, feasibility, okay, how realistic is it? And expected effectiveness. Yeah, this is also something I would say. This is rather guessing as a real calculation. So you see, this was now our first study by Stanford University. It is not so interesting here to understand what was exactly the result. Although in those 100 pages, they have a lot of data. It is a beautiful study. Read it, you will learn so much about the details. Great if you write scientific papers. This is a real nice one. But for our idea here that we compare this, we have to say, okay, nice. What do we learn from this study if we want to compare it here? Their main finding, and I have here chapter 7.2, and this is a screenshot for the original study. So this is the Stanford study itself. They came to the conclusion that LLMs cannot evaluate ideas reliable. And you know, currently we have in the community this idea LLM as a judge for evaluating everything, evaluating research ideas, the performance of other models, the performance of agents, and. However, Stanford says we offer now empirical evidence that LLMs cannot evaluate ideas reliability yet. And just look here at this very short table, and you have here in yellow, if you want the human performance here if you rate here the review score consistency, and in blue, GPT-4, you understand this is AI. Now, if we have random at 50, and you see here our best performing Claude 3.5 pairwise is 53, you have now an idea that compared to human AI conferences with a real expert, 71.9, there's now that the machines are not at all able here to do some reliable and consistent evaluation of those ideas. So LLM as a judge, big question mark. But what I found highly interesting is that Stanford decided here to include the AI scientist reviewer. And if you have seen my video here where I showed you PhD thesis in one day and open source AI, this is exactly it. By Sakana AI, University of Oxford, University of British Columbia, the Vector Institute and the Canadian Cypher AI chair, they developed this AI scientist. And this model could write papers, could do automatic scientific discovery, and communicate the findings. And they now in Stanford say, hey, if we use this from our friends at Oxford, we see, oh wow, so this has a real, not so prominent consistency rating. In fact, it is worst. So real nice that you have here now a cross comparison between the different actual models that we have for AI, scientific, whatever. So you see, sometimes we can smile if Stanford shows us here the performance of something from the University of Oxford. And now that we know this, now we have a deep understanding that AI scientists fail. And now we look here at the SCI, the Science Agent by MIT. And I hope MIT is a little bit, because now we know exactly what we have to look for. But you know what? MIT has some brilliant ideas in place. Those Science Agent is a system designed to automate the scientific discovery using, of course, multi-agent, intelligent graph reasoning frameworks. So what they do is something really nice. So I see here three components. At first, you have the ontological knowledge graph. So we map relation between concepts that may not be apparent to human researchers. Give you a background, we will take about 1,000 research publications and we try to find patterns that were not detected by human readers. Then we have, of course, as the core of our agent an LLM to process and retrieve information from the graphs and help generate research hypotheses based on these new identified patterns and connections. And then we have here, to increase, if you want, our reasoning capability, a multi-agent system where each agent has a little GPT-4 in the background as its main brain, if you want. And then we will look here at the team cooperation between multi-GPT-4 systems. So this is here the outline. Let's jump in. Now, the methodology is rather easy. So at first, we have a knowledge graph construction. So a large-scale knowledge graph. Now they here go MIT, particular on bio-inspired new materials, is created from thousands of research papers in this particular domain. And it organizes here the concept as nodes and the relationship as edges. And then we have a path generation within our network. So instead of finding here the shortest path between two elements, and I will show you an example in a minute, we don't go for the shortest one, but we go for a random path. This is a new strategy, and I will show you why this leads here to a broader exploration, enabling here the discovery of unexpected relationship that might not be the most efficient, might not be the fastest, but might be really valuable to discover new patterns. And once we have a multipath structure in a highly complex network, an LLM-based scientist, then an agent of course, uses now this extracted subgraph knowledge to generate now in plain English a research hypothesis considering elements such as the mechanism, the design principles, and the novelty. And then now comes the power of these multi-agent interactions. Now you have multiple GPT-4s, and they now discuss. And as you know, we have now one scientist and another scientist, and then we have a third scientist who is really critique. Says, I don't think that your idea was right, so it goes back and forth. They refine the scientific details, and you understand exactly what we are doing, like in a real review process where multiple professors sit around the table. And then we have a final output. Hypothesis is reviewed, critique, and finally refined for novelty and visibility. And we check, of course, again with the Semantic Scholar API, a function call, if this is a real novel idea. So let me give here you this visualization from the original paper from MIT. So we have here 1,000 publications. Then, and now comes the beautiful thing, with a sentence transformer, with an S-BERT system, yes, we generate here somewhere a vector place here, and we have an embedding, and we have, I don't know, 10,000, 30,000 nodes. I don't remember the exact number, but it's quite a lot of even more edges. And then you see here the connects between the node and the graphs, and you have identity and whatever. And so we have constructed our knowledge graph. I will tell you more about the process in a minute. And if we have here this knowledge graph, now the task is easy. We are given here by a human new task, a beginning and an end. And I will show you an example. And now we can have four parties. It could be human. Imagine this is a human research team. We have an ontologist, a scientist, another scientist, and another scientist that acts as a critique. Now, for my green grasshoppers, an ontologist is responsible for designing and managing the ontologies, which are structured framework to present knowledge about a particular domain. So ontologies consists now of a set of concepts, categories, and relationship that help define how knowledge in a specific domain is organized. Now you understand the task, why we have here an ontologist. Now you understand immediately that this is not restricted to 4 human beings, but we can build here 4 AI agents, each with a little GPT system in the background or multiple GPT system in the background. And I will have a look at this. And then comes the beauty. This is a predefined structure by me who coded this system. But I could also use here a new intelligence, and I say, hey, I will use here kind of it's not yet a swarm intelligence. This will be in my next or in my second next video. But we have now here multiple automatically defined agents. So we have here one planner. And the planner is here if you want the primary knowledge node here for decision making in this continuum, in this logical cell. And he says, okay, I need an ontologist, I need a scientist, I need another scientist, and I need a scientist that acts as a critique to the other 2 scientists. And if we do this automatically, it is up to the planner AI agent to say, hey, maybe I need to connect to the internet, maybe I need to connect to a database, maybe I need to connect to a supercomputer to run some numerical compute simulation, C++ on this for some physical background, for some material science background. So he creates an assistant with access here, you see this, to different tools. And the human, if there's a problem, planner comes back to the human and says, help, I'm stuck. So you see, highly interesting approach. Now, I told you about here how the process is that we come from 1,000 scientific papers to one knowledge graph. There are different methodologies, but I would like to recommend you this paper. If you don't know it, mid of June 2024, I think version 3 exactly, Accelerating Scientific Discovery by Generative Knowledge Extraction, Graph-Based Representation, and Multi-modal Intelligent Graph Reasoning. MIT, Markus Bühler, real nice. So for my green grasshoppers, the idea is simple. We go from the information, like here, 1,000 or 10,000 paper, to a knowledge representation, and we choose a knowledge graph representation. So you have here the text chunks, then you have structured raw, and then you generate the triples, and then you have multiple local graphs. You concatenate all the local graphs that belong together into some huge global assembled graph. Then you have a huge global graph, I don't know, in 1,000 dimension or whatever you like. And then you can do some graph-based reasoning on this particular representation. So great. Give you a very short idea, then you have a correlation of topics. You see, you have then dots that are, if you want, specific topics and how they relate, and then you have edges that have a specific functionality. A, B, C, D, beautiful. There's also a paper a little bit earlier in February by the same team, Erik Bühler and Markus Bühler, MIT. And they have something nice. They have a mixture of the low-rank adapters of LoRa, and they create a flexible framework for LLMs with application in the protein mechanics and the design. And what they do, and this is a nice idea, they start with a set of pre-trained LoRa adapters. You remember? The adapters, I have a specific video on this. And they propose here a gating strategy that using the hidden states to dynamically mix the adapter layers, allowing now the resulting cross-LoRa model to draw upon different capabilities and create never-before-used deep layer-wise combination of adaptation to solve specific tasks. So if you're into the topic, I would also recommend this particular paper to you, but this is just add-on. Now, back to the main topic. As I told you, if we have a starting point and we have an end point, topic A and topic B, normally in a graph we would find the shortest path and we would think this is the best connection. Now, if we want to find new ideas that are here somewhere close by, maybe hidden here and not discovered, so not part in the literature yet. So what we do? We take the same point here, we have here the other silk green point here, and then we look for other paths that are not the optimal shortest path, but there are also paths, random paths, and we do this for multiple paths. So we get an idea to go from the, let's say, epsilon environment of this particular node to the epsilon environment of this particular node, and we get a real good feeling about here all the transfer function here on our graph network, that what way can we go? What else is there in our place? Multi-scale organization, low temperature processing, biological materials. And you see, this is where the new ideas come from if we choose a vector representation, if we embed our ideas here in this particular way. Now, I told you already that we have here a predefined multi-agent configuration and flow. If you are exactly sure what your task is, and you know that this, for example, or maybe you have 5 scientists, and each and every scientist has a different specialization, domain, knowledge, then you go with 5 or 7 scientists. However, we are interested now in the case, what if we don't know the perfect combination of our team? So we don't have a human team, but we ask here an AI, an agent, to create here an AI team with, it's an optimization problem, of course, with a specific numbers, and let's see how many planner critique, scientist, ontologist, assistant we need here in our team network of AI assistants and AI agents. So let's talk about multi-agent graph reasoning system. And this is beautifully done by MIT, 80 pages, deep dive. I can give you only here the very surface, but it is really nice. So what they use here, so those agents here, they document the outlines of the entire process of automated scientific discovering using a hierarchical expansion strategy. What is this? I showed you that we have keywords as input and outputs. Here somewhere it starts and here somewhere in the graph it ends, and then we find all the random graphs. Now, what do? Exactly this. So they have initial keyword selection, starting point, they have the knowledge graph, a structured representation. The nodes represent concepts like I showed you biomaterials or energy efficiency, and the edges represent the relationships between them as stated in the scientific literature, because this was exactly one of the 1,000 or 10,000 papers that exactly explored here the relation between biomaterials and energy efficiency. So from the written papers, we create our network, we know now the graph structure, and then we do the path sampling. Means the system identifies connection, paths, if you talk about graphs, between the keywords within the knowledge graph, forming here subgraphs of related concepts and relationships. I already showed you this, but here you have it for migraine grasshoppers written down. So this particular subgraph will serve as the basis for generating now a structured hypothesis. Now, if we have the subgraph now, we need to generate here a structured output. And the output, we take JSON, but the content is now 7 points decided MIT. A hypothesis, so a scientific question or a claim generated based on the concept in the subgraph, the outcome, the expected result, if the hypothesis is tested, a mechanism, could be biological, chemical, physical mechanism, underlying the hypothesis, the design principle, novel, unique principle guiding the construction or the behavior of the system in the hypothesis, unexpected properties, new unanticipated properties might arise, comparison to existing systems, and a novelty. Beautiful. Third point, hierarchical expansion with individual prompting. Now we have the AI team coming in, the multi-AI agent, sitting around the table and saying, okay, let's discuss this. So each of the components, the hypothesis, the outcome, and the mechanism is then expanded during individual prompting. Maybe we have here our scientific agent number 2. Prompts are sent to the LLM or a specialized agent asking to refine each component by adding more details, more examples, more quantitative data, and so on. So we increase here the depth of our scientific knowledge and the precision that the scientific ideas now crystallizes. And then, as I told you, we have a third scientist, we have here a critical review process. You get the idea. And then they say, hey, maybe we need to do some numerical modeling. Everything is digital today, and even science. Or we do some computer simulation. Therefore, we have to have access via an assistant agent to some computational task, to a molecular dynamic simulation, whatever you have. Or we have to really to do some hands-on experiments. We have to use some synthetic biology, for example. We have to use some computer models. You get the idea. So here we have it, a summary, beautiful. So all of this process together automates now, says MIT, the scientific discovery. For my green grasshoppers, we start with the keywords, use the knowledge graph to map out a connection between the concept, generate a structured research proposal now in a specific JSON format. If you need a different JSON format, please alter this format. This is just an idea that MIT has for its material division. If you work in, I don't know, economy or finance, hey, you will have complete different template. Expanded proposal for more detailed and refined prompts, review it critical by another AI system, and produce now finally a comprehensive research draft that tells us exactly what we have to do. The overview of this autonomous agentic modeling is now more or less exactly as I already told you. It depends now, of course, on the causal complexity solution that each LLM is able to solve. And currently, GPT-4 is one of the best models on this planet for exactly this task, and it was chosen by MIT for this task. And you have, of course, autonomous agents to collaborate dynamically to create and refine research hypotheses for adaptive problem solving. You can have more. I told you this. The human, the planner, ontologist, scientist 1, scientist 2, scientist 3 acting as a critique. I told you about the assistant. And if you have problems and you have a conflict situation, maybe you need to put in a group chat manager who coordinates the interaction between the AI agent and chooses here. Give him his knowledge and give him his judgment and give him his, you got the idea, or better, its judgment. It will decide what agent has now the right to speak, to process the next step, and you got the idea. If you want to see this here in a flowchart, this is the flowchart for you. Planner, as I told you, this is exactly how the planner defines what to do. This is here the assistant. If the assistant has, for example, to assess the novelty, give it a score. Let's say it's 8 out of 10. Then you have here why it is exactly 8 out of 10. Or the assistant gets the task to assess the feasibility, give a score, explain why. You understand this is a standard. So for my green grasshoppers, short summary, the complete process here by MIT. Process starts with a plan developed by the planner agent. It involves creating a hypothesis based on the set of keywords provided by a human. The assistant executes the necessary function, generating a knowledge graph using keywords and analyze the novelty of the research idea. The ontologist agent defines the key concept and the relationships within the knowledge graph. Scientist 1 agent generates here the first initial hypothesis, and MIT decided to have here 7 key aspects, as I showed you: hypothesis, outcome, mechanism, design principle, unexpected properties, comparison, and novelty. Scientist 2 says, I expand on it, I make it even better. And scientist 3 then critiques, and then you can start all over again and run and iterate and loop, and you know the process. So just wanted to give you here the original visualization from the original paper by MIT. So if you have now multiple random graphs about multiple similar topics, close by topics, this is now beautiful to really find unseen patterns here, unseen parts in the graph that a human or the human reviewers or the scientist could not find out or not yet find. And the hope is that here our AI system just analyzing here the complete graph, going here for hundreds and hundreds of subgraphs to find here one single pattern that might be even better than all the other patterns that it already discovered. So what are the key advantages if we have now this autonomous agentic modeling? We have an adaptive problem solving, we have a comprehensive collaboration between our agents because each agent contributes here with specialized expertise. Yes, you can have for each agent a specifically trained and fine-tuned GPT-4 system, or you go with a little Llama 3.18b model that has been fine-tuned on expertise 1, and the other on expertise B, and the other on expertise medical. You can then combine them for a particular task, and the integration here of external tools. You have API calls, whatever you like to do, access to the internet, access to supercomputer, run C++ programs, ensure that a hypothesis generated about novel, that you compared with the literature, and feasible. Great idea, great implementation. And of course, I know a lot of you want to know the code. I give you here 2 GitHub repos with the Python code. I'm a little bit early, you see. MIT is currently uploading here the SciAgents here. When I started here, there was just README with 0 hours. So now README is up here 2 hours ago. It took me 2 hours to do here the complete video. And now I'm recording this at the end of this video. Only 1 star, 1 watching. Will be in short 2 star and 2 watching. But when you see this video, you should have the complete code here of the SciAgent discovery by MIT. As I also told you here, if you want to build those graphs from your document, from your whatever you have as data points, I think I give you also here the graph reasoning code if you want. Here you have graph reasoning and the notebooks here by MIT. This is really, really nice. Already, as I told you, published 3, 4, 5 months ago. Only 37 stars. This is really, I don't understand this, but I guess nobody noticed this and it was not hyped here on our platforms or whatever. But a real beautiful thing if you have huge documentation or you have a database. How do you build here a graph? Easy way to do. You have here the code. For the notebooks here, just 2 notebooks here, I show you a complete Jupyter notebook here with everything you need to know. We have a specific tokenizer model. As I told you, we have specific tokens. I have all the videos about this. They even give you here a visualization of the different clusters. They go with a simple methodology. If you want to go with a little bit more advanced, you find this in my videos, never mind. And for the graph reasoning here, for the graph generation, it's a simple Python file. And for the graph analysis, is also a simple Python file. So the code is out there for you. You can use it. No problem at all. Whenever you see this video, I think 1 or 2 days later after I record this, you should have the complete code available for you. So today we looked here at 2 real different implementations of AI agent in science. One implementation was from Stanford University, the other implementation was from MIT. MIT was really focusing here on a more diverse multi-agent environment with all the tool use, with all the different function calling functionalities. Real interesting how you combine those multiple agents here to build a team, a virtual team to solve the problem. Given how you build here your knowledge graph, not from a single paper, from 10 or from 1,000 or 10,000 papers, you have the code, you have the implementation. I hope I explained it a little bit to you. I have given you all the research paper that I would recommend if you start new that were real helpful for my understanding. And I think now it is up to you to go and say, I don't know, Corsa AI, hey, this is the GitHub repo that you have to learn. Upload this GitHub repo, understand how the coding is done by MIT, by Stanford, and now you can implement it, and Coda AI might be able to write your own code for your own problem, for your own example, for your own app, integrating now all those brand new ideas just published 1 and 2 days ago. I hope you enjoyed the video. I hope you find something interesting, and it would be great to see you in my next video.